All right, our next topic is to talk about continuous distributions. This is different from discrete distributions or binomial distributions. This is going back to what a continuous random variable has to deal with. And this is relevant anytime we're taking a measure of some sort of data, and the numbers themselves can be as many decimal digits of accuracy as we want. So time is something that we might consider to be a continuous random variable. Um, and let's see, our numerical variables, whose values fall within a range or interval, and our measurements, and then be described by a density curve. Now, of course, what is a density curve? A density curve, and we'll look at some illustrations here in a moment, is a graphical representation of all the possibilities within this set of data. So we typically draw it in what's known as the first quadrant, and we're going to look at using some geometrical formulas to calculate it at first, and then we'll broaden out to some other types of shapes. But we define it to be the area on or above the horizontal axis. The area is equal to 1, and that's specifically because we use the area to represent the probability of an event occurring. And as we know about from the probability unit, the likelihood of all the sample space is 1. And when we talk about the area under the curve, we're looking at what proportions of the observations fall within a given range of values. So we're going to kind of help develop this idea of what we mean by density curve by looking at some unusual density curves, for lack of a better way to do this. And these are things that we can use some geometry formulas to help calculate the area. So we're going to start with a nice triangle. And the question is, what's the, so if this particular triangle has a base of 4 and a height of 0.5, if this represents the probability of a given situation, what's the probability of an event occurring less than or equal to 2? So we're looking at this little region right here, which is a sort of a triangle within a triangle. And the question then becomes, well, how do we actually calculate an area of a triangle? Well, that's just base times height divided by 2. So looking at our picture, we've got a base of 2 and a height of 0.25. And so I was kind of showing you the calculation there. 2 times 0.25 divided by 2 gives us a probability of 0.25. So in this sample space, in this event, of some whatever less than 2 represents, the likelihood of that event occurring would be 25% of the time. Okay, well, let's add another question then. What about exactly at 2 versus less than 2? Well, less than 2 goes back to that same picture we just saw. We've got a base of 2 and a height of 0.25, so it's still a triangle. But what about exactly at 2? Okay, and really what I'm asking when I say exactly at 2 is I'm asking for the area of a line segment. And you got to think, a line segment doesn't have, it has a length, but it doesn't have a width. In order to find an area, you need to have a length and a width of some kind. So for a equal event in a continuous distribution, you don't have that event occurring. That's kind of weird to think about, given that this particular sample space is anything between 0 and 4. We're saying at a particular value, the likelihood of that occurring is 0, and yet I can add up a bunch of these zeros. In reality, if you think about it in terms of time, so let's say it takes 4 minutes to get somewhere, what's the likelihood of you showing up exactly at 2 minutes right on the dot instead of 2 minutes 1 second or 1 minute 59 seconds? When you start looking at a range of values, that starts to have a probability. But the likelihood of you running into the door exactly at the 2-minute mark isn't very likely at all. Almost impossible to get an exact time, but a range of times you can actually have. Okay, but the point is, In a continuous distribution, the less than and the less than or equal to are considered to be the same. That's distinctly different than discrete. In discrete, these would be viewed as two different events. Okay, so let's kind of continue with our geometry exploration. Let's say I give you that same triangle shape, but this time I would like to know anything greater than or equal to 3 versus anything between 1 and 3. So you got to think, how can I break these shapes up, especially if I'm looking at anything from, say, 3 to 4 or between 1 and 3. Both cases, those are trapezoids. Okay, and so the area of a trapezoid is 1/2 height times base 1 plus base 2. So we just need to go into our picture, figure out what the two bases are, multiply by that by the height of the trapezoid, and then divide that by 2, and we get the overall area. Okay, so I've gone ahead and sort of filled in the numbers for us here. For the one that's greater than or equal to 3, so here we are, 3 to 4. That height happens to be 1, and you've got one base that's going up. And you got to think, how do we get 0.375? Well, at 4, I'm all the way up at 0.5, which is one of our other bases. If at 2, I'm at 0.25. So what's halfway between 0.25 and 0.5? Let me kind of pull out a calculator here and show you that. In case we're like, what is he talking about here? So if I want to know halfway between 0.5 and 0.25, so if I add up those two values and then divide that by 2, that's where I'm getting that 0.375 from. So at 3, the lower base happens to be 0.375. So that's enough numbers that we can calculate the area from anything bigger than 3. Between 1 and 3, okay, now where'd the 1.25 come from? Well, here's 1, and I know at 2 it's 0.25, so I want halfway between 0 and 0.25, and I can take a calculator out again and just divide 0.25 by 2, and that's where that 0.125 bar comes in. And then I would type in, just type in that in the formula. Okay. Let's change shapes. So this sort of strange looking object, I would like to know the probability of anything greater than 1. So think about what kind of shapes make that up. And that looks like some sort of square, maybe a triangle region. Let's see, for a square, sorry, down here the square, we've got a base of, starts at 1, goes to 3, so it's got a length of 2, and it's got a height of 0.25, so that's how we find that area. For the triangle, again, it's got a base of 2, because you go from 1 to 3, and then it goes up, sort of, if you remember your geometry days, the altitude of the triangle happens to be 0.5, and then I want to divide that by 2. So 1/2, I'm sorry, I'm going to take that back. It starts off at 0.25, you end up at 0.5, so that's where that height happens to be 0.25. And then if I want to find the overall area, just add those two numbers up, so 0.5 and 0.25. Okay, let's change the question again. This time I'm going from 0.5 to 1.5, so 0.5 is not even on the picture, neither is 1.25. I'm sorry, 1.5. If you think about the shapes that we're generating, though, we're looking at a rectangle and we're looking at a trapezoid. So let's talk about the rectangle then. Rectangle is base times height, length times width. That would have a width of 0.5 when it's got a height of 0.25. So if you multiply those two numbers together, you get the area of that rectangle. And then here we've got another trapezoid. The height is from 1 to 1.5, so that's where we got the 1.5 there. The first 0.5 is in the formula. And then I need to know the heights of the bases. So the lower base we can see in the picture is 0.25. How do we get this one right here, Well, let's look at what we do know. I do know at 1 it's 0.25, and I do know at 2 it's 0.5. Well, what's halfway between those two values? So that's add them up, divide by 2, and we get to 0.375 again. So when I type in all of that formula in the calculator, I get an area of 0.156. And then I just want to add the two numbers together. So that would give a probability of 0.28 to be described in that particular event.